Mesopotamian pantheon gods began with the Sumerians. Many of these gods were tied to the planets. This idea was carried on by the Greeks and Romans. Mesopotamians used a sexagesimal system of measurements. This is why we measure circles into 360-degree segments today. This system is still used by today's astronomers to plot cosmological phenomena. Babylonians used the heavens to establish an accurate calendar to track seasonal welfare of agriculture. They built pyramid-like structures called ziggurats with 7 terraces, one to represent each the Sun, Moon, Mercury, Venus, Mars, Jupiter, and Saturn. The Egyptians used astronomy for developing calendars to predict the Nile flood. They also used astronomy to align temples and monuments using cardinal points like north, west, east, and south. Stonehenge exhibits alignment with the sun and moon. The main axis faces the horizon where the sun rises midsummer morning, although it's not exactly lined up. The Chinese used astronomy to figure out how long the year was. They had records of 900 solar eclipses and 600 lunar eclipses carefully recorded for about 2,600 years. They recorded meteor showers and comets as guest stars. Thales predicted a total solar eclipse that took place during a battle between the Persians and Lydians, even though, before him, no one else was able to predict a total solar eclipse.
Pythagoras was famous for forming a group named the Brotherhood of Pythagoreans that was devoted to mathematics. He believed that numbers ruled the universe. Pythagoreans gave many ideas and objects numerical values. Pythagoreans discovered that if 2 legs of an isosceles right triangle are a measure of 1, then the hypotenuse is square root of 2. He came up with a Pythagorean theorem, which is a squared plus b squared equals c squared. Babylonian temple astronomers called Supar and Numa Anu and Nil observed the skies for centuries and recorded their observations in astronomical diaries, almanacs, catalogs of stars, and other texts. The data recorded by Babylonian astronomers were the length of the synodic month, or the period between 2 full moons, and the length of a year. Babylonians were able to predict lunar eclipses and solar eclipses later on, with a fair accuracy with this data. The tool they used was a cycle, a period of 223 synodic months, or 18 years and 113 days. Babylonian astronomers discovered that 235 lunar months are identical to 19 solar years approximately, and they concluded that 17 out of the 19 years ought to be leap years with an extra month. Aristotle studied under Plato. He believed in a geocentric universe and that stars and planets were perfect spheres except the Earth. He also believed that the movements of stars and planets have to be circular since they were perfect spheres, and they could go on forever. His teachings were respected by the people, even though later on they were proved to be wrong. Aristarchus applied geometry to astronomy shortly after Euclid wrote his famous book on geometry. The method Aristarchus described for determining the distance to the moon required the moon's linear diameter and angular diameter. He also used lunar eclipses to figure out how to measure the size of the moon by measuring the duration of time between the moment when the edge of the moon first entered the umbra and the moment when the moon was totally obscured. He believed that the sun and the moon have the same angular size and that the sun must be 19 times bigger than the moon. Eratosthenes used geometry to estimate the circumference of the earth. He measured the altitude of the noontime sun at Alexandria at its maximum on June 21st. On this date, the sun is directly overhead at noontime in Syene in southern Egypt. The latitude is 23.5 degrees. He measured the tilt of the Earth's axis by 23.5 degrees, giving us seasons.
In 134 BC, Hipparchus discovered a new star. He estimated that precision shifts the vernal equinox about 1 degree every 78 years and completes 360-degree cycles every 28,000 years, which is within 10% of the actual precision period of 26,000 years. The Mesoamericans built their monuments to align with sunrise and sunsets at the equinoxes and solstices. Important events were set up to coincide with particular positions of Venus. They predicted extremely complex dates in advance, like solar and lunar eclipses and the rising of Venus. Ptolemy worked in Alexandria. He created a system of circles to plot movements of planets, invented terrestrial latitude and longitude, and gave coordinates for 8,000 places. He was the first to make maps with north at the top, and he finished the model of the solar system that Hipparchus had worked on. The Arabs and Muslims studied the sky for timekeeping and used astronomy for religious reasons. Copernicus created the heliocentric solar system and was the one who made the system with the sun in the center of the solar system instead of the Earth being in the center.
Tycho Brahe believed that the supernova he observed in 1572 was a new star. The star was visible for 18 months approximately, before fading from view. This created a change in the sky, leaving a prevailing opinion that the supernova was not really a star, but some local phenomenon in the atmosphere. In 1577, he made careful observations of a comet. He was able to show that the comet was further away than the moon by measuring its parallax. This observation contradicted Aristotle's teachings. Galileo's observations aided to the triumph of the heliocentric model. With this telescope, he observed a remarkable phenomenon that no astronomer could have seen with the naked eye. When he looked at the Milky Way, he discovered that its glow was the combined radiance of myriad stars, so faint and so close together that they couldn't be distinguished with the naked eye. The sun, moon, and other celestial objects were generally thought to be smooth, perfect spheres before Galileo observed them. Kepler believed in the Copernican system firmly, unlike Brahe. He was forced to realize that the orbits of planets aren't circles, but rather ellipses. For every ellipse, there are 2 points called foci, or singular focus, such that the sum of the distances to the foci from any point on the ellipse equals a constant. In other words, A plus B equals constant. The amount of flattening of the ellipse is called eccentricity. Ellipses become more eccentric from left to right in this picture shown. A circle can be viewed as a specific case of an ellipse with zero eccentricity. All ellipses have eccentricities ranging from 0 to 1. One must carefully measure the geometry for most planets to determine that they aren't circles, but ellipses of small eccentricity. The long axis of the ellipse is called the major axis. The short axis is the minor axis. Half of the major axis is called semi-major axis. The length of a semi-major axis is often the size of the ellipse. The average separation of a planet from the sun as it goes around its elliptical orbit is equal to the length of the semi-major axis. Kepler's first law suggests that the sun isn't at the center of the ellipse, but at one focus, with nothing at the other focus, and that the planet then follows the ellipse in its orbit, meaning that the distance between the Earth and Sun is changing constantly as the planet goes around its orbit. His second law suggests that the line joining the planet to the Sun sweeps out equal areas in equal times as the planet travels around the ellipse, so the planet moves faster when it's closer to the Sun. A planet executes elliptical motion with constantly changing angular speed as it moves around its orbit. The point of nearest approach of the planet to the Sun is called perihelion. To sum up his second law, a planet moves fastest when it's near perihelion and slowest near aphelion. His third law suggests that the ratio of the squares of the revolutionary periods for two planets is equal to the ratio of the cubes of their semi-major axes. It also implies that the period for a planet to orbit the Sun increases rapidly with the radius of its orbit. Sir Isaac Newton used to write his ideas in a journal when he was in college. He had ideas about motion, which were the 3 laws of motion, gravity forces, and the diffraction of light. Newton's first law states that an object in motion will remain at motion, while an object at rest will remain at rest unless acted on by an outside force. Newton's second law suggests that force equals mass times acceleration. Newton's third law states that for every action there is an opposite and equal reaction. Edmund Halley was able to come up with the conclusion that solar heating is behind atmospheric motion. Most of his time was spent conducting lunar observations. He first made calculations with comets that orbited Kirk, and he was able to make use of flamseeds. He was able to calculate the orbit of the comet in 1682. However, his calculations weren't too accurate. The comet bears his name today.
Einstein's special theory of relativity extended Newtonian mechanics to large speeds close to the speed of light. He describes changes in measurements of physical phenomena when viewed by observers who are in motion relative to the phenomena. Niels Bohr created the Bohr model of the atom. He proposed that energy levels are discrete and that electrons revolve in stable orbits around the atomic nucleus but can jump from one energy level to another. Werner Heisenberg did research with Niels Bohr and developed matrix mechanics formulation of quantum physics. He also won the Nobel Prize in Physics. Wolfgang Pauli also received a Nobel Prize in Physics for his discovery of a new law in nature and the Pauli principle, involving spin theory, which is the basis of the structure of matter. Edwin Hubble showed that the recessional velocity of a galaxy increases with its distance from the Earth, implying the universe is expanding, known as Hubble's law. He provided substantial evidence that nebulae were actually galaxies beyond the Milky Way.
George Lemaitre is considered to be the father of the Big Bang Theory, which is the theory that the expansion of the universe began with the explosion of a single particle at a definite point in time. His idea first appeared in a paper by him in 1931. His idea was hard to believe by astronomers at the time. He kept his religious life and scientific life separate. Robert Oppenheimer was responsible for creating the atomic bomb. He witnessed the first explosion of an atomic bomb in the New Mexico desert on July 16, 1943. Fred Hoyle is remembered for his contribution to the theory of stellar nucleosynthesis, and he rejected the Big Bang Theory. He was also well known for his steady-state cosmological model. In 1964, Bell Laboratory scientists Arnold Penzias and Robert Wilson created a horn antenna that picked up cosmic microwave background, or CMB. Initially, they were trying to detect sources of radiation that may potentially harm satellites. Their data showed a background noise from a microwave signal at approximately 2.7 Kelvin. Their discovery supported the Big Bang Theory. Buzz Aldrin and Neil Armstrong were the first humans to land on the moon on Apollo 11 on July 20th, 1969.